nanomolar. So the y-axis can change. In this particular case, it's fluorescence. Fluorescence is often arbitrary units. But you do all manner of things, so don't get too caught up into the method. Just the fact is, you have a spectroscopic response as a function of a free ligand. All right, what's the max? Divide by 2, go across, go down. I should be able to get a KD out of it. The only other thing to note is, is it a kind of normal plot, or is it some kind of log-log plot, in which case we'll have a line, something like this, right? And now, if I'm plotting log f over 1 minus f over log L, I'm doing it differently, right? I'm basically looking for the point where it's crossing 0 and going down. But to remember, right, this isn't log, so I'd have to take the anti-log. I'd have to take 10 to that power and get the association constant happening. So lots of methods. Some people don't like fitting these types of plots, but like the lines better. It just depends. All right, so a couple other examples just to show you that that spectroscopic response can be anything. It could be radioactivity, it could be fluorescence, it could be, in this case, so my group is really interested in how proteins bind and metabolize fats in some cases, because we can actually convert them into fuels. Here's a protein that does it. This is actually really good. It takes the carboxylate from fatty acids, clips them off, and actually just will make gasoline. So we're excited about that. It's a heme protein, so a nice red cofactor. Here's the fatty acid that's binding the pocket, just shown in kind of space filling model. All right, so here is kind of looking more closely at it. Here's the heme cofactor. You don't have to really memorize that, other than the fact that it has a red color. The fatty acid chain, I should have colored it differently, but here's the fatty acid chain that's kind of going into the active site. All right, so what is stabilizing this fatty acid in terms of interaction? I've highlighted some of the residues. What types of amino acid side chains do you see? Polar or non-polar? What would you expect from something greasy like a fatty acid? Big fatty acid, big carbon chain. It should be pretty non-polar, right? All right, so if I look around, what amino acids do you see? What's this guy? Phenylalanine. What's this guy? Also looks like a phenylalanine. So you look around here, right, and it's got really non-polar. That makes a lot of intuitive sense. Substrate is really hydrophobic. If I want the substrate to find this site and be stabilized, lots of hydrophobic interactions. So it's not just about protein folding, right? It's also about ligand binding. You match the environment for the ligand. All right, so what do we think about the dielectric constant in the active site for this protein? High or low? Does it look more like benzene or more like water? All right, let's put it another way. Does phenylalanine look more like benzene or more like water? Benzene. Looks a lot like benzene, right? All right, so dielectric constant is high or low? Water is 80. What's vacuum? 1. All right, what are we closer to? We're closer to 1. We're not quite vacuum, right? But we're pretty hydrophobic. Benzene would probably be a pretty good model of this active site. All right, so here's another interaction that we see. I'm just trying to combine concepts of what we learned. All right, so here is, what residue is this? We have one of two options. The blues are nitrogens. Yeah, so this is an arginine. Here is the carboxylate of the fatty acid. So what type of interaction is this? It's probably some hydrogen bonding, but otherwise there's a nice charge-charge interaction. This guy is positively charged. This is an acid that's negatively charged, at least at this pH. All right, so it's a charge-charge interaction in a really hydrophobic site. What do we think? Is it strong or weak? Strong. Pretty strong. What if I did the same thing on a surface? Would it be stronger or weaker? Weaker. So if I put that on the same kind of interaction on the surface of the protein, my dielectric is much, much higher. Remember that these coulombic interactions all scale, right, are inversely proportional to epsilon. We had it on the last test, and that would be much weaker if I put it on the surface. So if it's buried in a hydrophobic site, I should probably be pretty tuned to it because it's probably a pretty good interaction. So, does the environment matter? Yeah, the environment matters. All right, so here's real data from a paper. This is the absorption spectrum. This is just a UV visible spectrum of that particular protein. This is now just binding, so here's the substrate-free spectrum in black. And what my student did was just add fatty acid, ultimately ligand to it, and you see some change. We don't have to go into the inorganic chemistry of why there's a change that happens, but there's a change that happens in the spectrum. Ultimately, it's some change in the ligand environment, but it results in some color change, which is great. So this is a really easy optical spectrum that I can take. All I have to do is titrate my ligand, and I should get some spectroscopic response. Hopefully, he should be able to get a KD out of it. All right, so he did. So what he does is he plots the change in absorbance as a function of fatty acid. This is just a C20 K-1 fatty acid, it doesn't really matter. And he fits it to an equation like this. So notice that there's some change in absorption, and basically this is just a permutation of the L over KD plus L. Right? This substrate, in this case, that's L, KD plus substrate, that's KD plus L. A mass is basically where this thing will ultimately saturate out. So you can use all different types of measurements to do it. In this particular case, the protein affords the spectroscopic label, which makes it really helpful. In the tryptophan example, it's very similar, right? Because tryptophan changes environment when the drug binds. That's useful if I can measure it. All right, so if I look at and wanted to determine the KD in this beautiful example that he took, where's the KD around? It's micromolar on the x-axis. So where is it max? It maxes around what, 0.4-ish? So I go to 0.2, I go down, and it's somewhere around 3 micromolar or something. Now, here's the problem with this particular experiment. His protein concentration is also at 5 micromolar. And so I'm going to tell you right now, this is not the equation that would result in a really good value for the KD. And the reason is that the KD is very close to the protein concentration. So, what we do in these experiments, and he had to go back and kind of reanalyze the data. When we're doing these plots, on the x-axis, what we are plotting is we're assuming all the ligand is free on the x-axis, or at least most of it. So this is what's called the free ligand assumption. So what we're assuming is that basically, so experimentally, if I do a titration, do I really know L free, or do I know L total? So just think about it experimentally. I'm titrating something in. Do I know free or do I know total? I know total, right? Because that's what I added. All right, so our assumption in this free ligand assumption is that free is basically equal to total. All right, so sometimes that works great, and then sometimes it doesn't work great. All right, so the other, the corollary to that is, what I'm also assuming is that the amount of ligand that's bound is much, much smaller than the total. That's just another way of saying on the x-axis, I think most of it is free. Most of total is equal to free. All right, another way to put it, basically I'm assuming L total is around L, so that's fine. So that's assuming the free ligand concentration is essentially the same as total. Sometimes that holds up great, but then there are some occasions where it doesn't hold up so great. So here it is kind of graphically, because this will probably make more sense than those equations. So on the top is a situation where the free ligand assumption is true, meaning that if I look at adding all this, right? Most of my ligand, all the free stuff is basically the same as the total, right? Very little of it is down to a protein. So that's a situation where we can use a normal kind of analysis, no problem. Now, if it's not correct, and in this particular case of the measurement he did, it's not correct, things become more complicated. And basically things become more complicated because a lot of the ligand is now bound. And so as a result, L free is not equal to L total anymore. All right, so free ligand assumption good, free ligand assumption doesn't work. So we need some other type of way to analyze the data. And basically we need a way to analyze the data where we don't assume that we know anything about L free and L bound. That's our problem. All right, so that leads us into a different type of analysis. And it leads us into what will look like a really bad equation at first, but I'll show you the derivation and you'll see it's not so bad. While I ask you to derive it, no. But I want to show you that the derivation is pretty simple. So this is what's called the Morrison equation. It's a thorough way to treat binding equilibria. You can use it on any system. So you don't have to exclusively use it on systems where the free ligand assumption doesn't hold. You could use it on any, but it's particularly useful for those. All right, so what's the important thing about it? The important thing is I don't need to know anything about how much of my ligand is in the free ligand state. When we look at the equation, notice that you won't see L's by themselves. You won't see that at all. So So it's completely independent of the free ligand assumption. That's the beauty of the derivation of it. So experimentally, I know L total, because that's when I do an experiment, I hopefully know the concentration of what I'm adding. All right, so it's useful. All right, so particular example. In the example that I showed you, that my student did, basically he had to use it because the KD is numerically really tight or numerically small or very, very high affinity. So in our particular case, it was nanomolar or lower. Another case where you might think about it is if I have an experiment and it requires really, really high protein concentration, you might think you might have to need it because let's say I don't have a lot of ligand or it's not very soluble. Basically, that would result in a situation where my free ligand assumption it doesn't hold up anymore. All right, so all that being said, here's the punchline of the equation, and I will quickly talk about where it comes from. All right, so what I am plotting ultimately is my protein ligand complex over total protein concentration. And if I look internally, I see that all of my protein concentrations are in the form of total protein. That's fine, it was before. But look at what my ligand now is. So do you see any free ligand terms in this equation? You see any L's by themselves? They're all L totals, right? Versus all the hyperbolas that we did before, right? All these. These are all essentially free. So that's the critical difference. We assume that they're total because that's what we know, but this type of analysis assumes that most of it is free. All right, so that's the utility of it. Now, the question is, all right, where does this come from? Yeah, it looks long, but the big thing is that it doesn't require any knowledge of free ligand. All right, so to derive it, what does it ultimately look like? Does it look like any equation that you've come across before? Boom, quadratic. All right, so it's a simple solution of a quadratic equation. Now, that's the biggest hint. Just for ease, I'm going to call, I don't want to do things in terms of P and L and stuff like that. I'm just going to do things in terms of simple reaction of A plus B going to some AB. This will have the dot in it, but I'll probably omit it because I don't want to do it. All right, so with this type of generic equation, what is my KD equal to? What's in the numerator? This is really the same as this. Okay, so what's on the numerator if I want to numerically do my KD in terms of A and B? All right, so that's going to be the concentration of A, the concentration of B, and then what's in my denominator? A dot B, or just, so I'm going to leave out the dot, but just simply AB. Okay, so here's where the fun comes in. If I want to figure out what free A is equal to in terms of total A and AB, what would that be? So what would free A be equal to? Let's say it's going to be some A total, right? Minus what? Minus AB. All right, so same deal with B. So one might be protein, one might be ligand. That doesn't matter. So that's going to be the same, right? B total hot minus what's bound AB. All right, so that's the first step of it. Now, what I'm going to do is just simply take these and put them in there. So now, my KD is just simply going to be equal to A total minus AB, B total minus AB. I'm going to keep the bottom the same because I haven't done anything with that. And that's just over 80. All right, everybody's following there. Simple substitution, right? Okay, so what I'll do next. I'm going to multiply everything. I'm basically going to take this out and put it over here. So everybody have that before I erased it? That was AB on the bottom. Okay, so instead of KD, I'm now just going to make this KD AB. All these are concentration. I don't feel like drawing the brackets over and over again. All right, so how am I going to deal with the thing on the right? I want to multiply that out. So how do I multiply this out and get all the terms? Foil. All right, so if I foil this, first outside, inside last, right? What I'll get is A by B, T is total. ATBT minus AT AB minus BT AB plus last AB times AB, AB squared. All right, so now it's kind of starting to look like a quadratic equation. All right, except this is all in AB. All right, so if I want to look at this in terms of something that I can solve using the quadratic equation, what should I do? What does the left side of the equation have to be equal to? 0. All right, so let's make it equal to 0 just by doing this. All right, so now all I'm going to do is I'm going to take all the terms that have AB in them, this one, this one, this one, and I'm just going to rearrange it in a way. All right, so simple rearrangement, 0 equals, I'm going to make it look nice. 0 equals AB squared minus AT AB right, so now it's really looking like a quadratic, right? Meaning that if I think about it this way, right, this is the form of ax squared. This is the form of bx. This is the form of c.
What's the last term?
Oh, the last term is AT/BT, sorry. I'm running across, so it was small. Okay, so what is x? What is the same between this guy and this guy? That would be x. Sorry, I pointed right to it. So x is just simply AB, right? Which is squared. All right, so what is a? What's the a term? 1. Okay, what's the b term? The b term is this whole business in here. And this c term is essentially a total, b total. So that's the derivation. So once I have that, that's where that big Morrison comes from. So now, the punchline of the big punchline of it is that there is no free ligand assumption. All the ligand is in terms of L total. Experimentally, I know what that is. So, all right, here it is kind of graphical. And what I've done is, here's a protein concentration that I do an experiment, it's at about 10 micromolar. And what I'm doing on these graphs is just saying, okay, here's fraction bound, here's some ligand concentration in micromolar. Normal type of plot. Now, I'm going to change the dissociation constant from 100 micromolar to 0.1 micromolar. So, what do you see for the shapes? As the dissociation constant gets better and better, what do you see for the shapes of the plot? They kind of have a funny shape. Look at the green and pink one versus the black one. All right, so what you see for these guys with really high affinity is they kind of start, instead of being the nice kind of hyperbolic curve, they start squaring off. They almost look like two lines. Not exactly, right, but they start looking like that. That is a pretty good indication that we have really tight binding and we would need to use the Morrison equation. All right, so here it is graphically when you have really good binding. So you see how they're really, really squared off? So in this case, I've changed my KD is constant at 0.1 micromolar, and I'm changing the total protein concentration. So just note, like, when you see these kinds of things that almost look like two lines rather than a nice smooth curve, that's a really good indication that I need to use the Morrison. Or another way, you can see, like, I've changed the protein concentration, and you can see it saturates basically at the point of P total, meaning that the free ligand assumption's never really working in this particular case, which is why you have to use that analysis. All right, so another interesting scenario that we might have. So that's kind of one problem. If I have a really tight binding coefficient, I can't use my hyperbolic equations, my normal favorite ones, I have to use Morrison. Another real experimental problem is, notice that all of our kind of fun facts, right, always required knowing something about protein concentration when we do this experiment. But you could imagine a lot of situations where you don't know what the protein concentration is. Let's say you were doing something in cell lysates where there's a ton of proteins and there's no way to measure the protein of interest. It would be nice to still be able to measure dissociation constants if we could. And it turns out we can. So here's some example. This is some impure protein, let's just call it, and we break open the cell, we're looking at receptor, we don't know what the protein concentration is. We're going to use our same kind of assay where we take, in this case, this is retinoic acid, but it's spiked with radioactivity. We're going to add You know, in this case, we're going to add some charcoal pellets, and we're going to be able to pellet it out selectively. And then basically what we're doing is we're removing free ligand from the protein stuff, and then we can basically measure the receptor and the receptor that's bound to the ligand. So it's just doing it in a slightly inverse way, but it should work. So the protein solution could be, in this particular case, is a mess. So there's no way that I'm specifically isolating my protein of interest. There's just a lot of stuff in there. So I don't know anything about my protein concentration. This is a real problem that you could encounter. So instead of doing it kind of in a normal, kind of nice way that we do, we can do what's called a stature analysis. Here, all right, so here is stature. So I'm starting from the same place as always. My KD is simply equal to my protein concentration, my ligand concentration over the complex. All right, so nothing fancy there. What I'm basically doing is a very similar permutation where I'm just saying, hey, my free protein is simply equal to my total protein minus what? Minus the stuff that's bound up, right? All right, free is equal to total minus that's bound. All right, so basically, what I can do is start thinking about combining, and ultimately, and I'm going to rearrange and do various other things, but I'm going to end up arriving at an equation like this. So basically, L bound over L, or you could think about it as L free, is equal to my total protein minus my bound ligand over my KD. All right, so this is useful because now what I'm looking at, instead of I'm basically just focusing on the ligand. How much is bound and how much is free. Because I don't know much about the proteins. All right, so the reason that's very useful in some ways it's exactly that. I'm looking at it from the context of the ligand rather than the protein. All right, so here's the plot. Here is now plotting bound ligand over free ligand over some bound ligand. And what that means is this relationship, that's basically what I'm plotting. Here's my Y, and then I'm just plotting L bound on my X. So if I want to determine, I can determine a lot of things from this, which is really helpful. Here, if I take the slopes, and now notice that this is a nice, beautiful line, negative slope. The slope of this line in a scatter plot is negative 1 over my KD. All right, so that's useful. I still get the dissociation constant out. All right, regardless of the fact that I don't know anything about protein concentration. The other really nice thing about it is the y-intercept is really informative, because that gives me my total protein over my KD. All right, so if I combine those two things, that's pretty powerful, right? Because I figure out the KD here, I use the intercept, well, I already know what the KD is from this. That means I can figure out what my total protein concentration is. So it's useful, right? So let's say we had a lysate with millions of proteins. I have no idea what the receptor concentration is. I can do binding titrations. Hey, I can figure out how much receptor is in there. That's really useful. All right, so here's the question I want to give you guys. So the end of class, that hand in. All right, I don't know what I'm gonna do with it, but let's try it. So I want to give you a pharmacology question. All right, so this is MRSA, right, which is a really nasty group of, so what is MRSA? All right, methicillin-resistant staph aureus, right? Huge health problem. You go into a clinic, the first thing you do is get swabbed, right, and they're testing you for MRSA because they're tough to combat. All right, here's a common, I'll give you the kind of drug backstory, and then we'll go. So this is vancomycin. This is commonly used to treat MRSA. It's by no means the only thing, but it's pretty effective. It's what's called a glycopeptide antibiotic, or GPA. The way that GPAs work is by inhibiting cell wall biosynthesis of these pathogenic bacteria, right? They're gram-positives. And basically what they do is they target an enzyme called glycosylase. All right, so here's the question, clinicians. All right, so somebody comes in, right? They have a MRSA. All right, you have to treat it, right? All right, so you're going to choose vancomycin with vancomycin by injection. All right, how much are you going to give? Don't say 1 liter. Can't do that. It does have toxic byproducts. All right, so what do we need to know? Let's put it this way. What would you like to know as a clinician in order to even be able to approach this?
Concentration.
All right, so you probably need to know something about concentration, effectiveness, something, right? All right, so I'm just going to show this off. All right, so here's the question. How much vancomycin will I give? All right, so vancomycin binds some enzymes. You don't necessarily need to know what the name of it is. So what would you like to know about it?
How effective is it binding?
I would like to know the KD. All right, so the KD of vancomycin to its target is, I'm going to tell you, I looked this up, I Googled this, 25 nanomolar. It's pretty good, actually. Pretty good drug. All right, what else do you need to know? I want you to determine vancomycin in terms of a real dose, meaning I want it in terms of milligrams. I want to see how close we come to the actual prescribed dose. I don't know how well this will work. Molar mass. All right, molar mass. You do need to know that. Molecular weight is 1,500. All right, what else do you need to know? So you probably need to know something about how much do I have to inhibit that enzyme in order for it to be effective. This is the one I made up. I'm going to say if you inhibit it by 7, so basically if you, I'm going to put it in easier way. If the fraction bound of the target is 0.75, meaning it's 75% bound, good drug. I'm not looking for 99%. That number I kind of took out of my hat, but thinking that's probably decent. All right, so what's the last thing you need to know? You're going to have to go to milligrams eventually. You need to know volume. All right, so volume of human bloodstream. What do we think, roughly?
7 liters? Isn't it 7?
Whoa, 77 liters is a lot.
No, 7 liters.
Huh?
Isn't it 17?
Yeah, average is 4.5 to 5.5. Let's just go 5 liters. Now, there's assumptions in there all over the place, I know. 25 nanomolar is real, molecular weight is real. 0.75 is my assumption. 5 liters is about right. It's probably going to depend on the weight, the actual size of the person, but it doesn't vary that much. All right, so this might be too long for 5 minutes. So take this one home, hand it in next class. Yeah, hand it in next class. You have some time to work on it. I want to see how close we get to the prescribed dose. Don't look up the prescribed dose. Well, I'm curious. I know what the answer in the clinic is. The answer in the clinic is somewhere like 200 milligrams. But de novo, with all this information, we'll see if we get there.